I make you the host.
If you want, whatever, it doesn't make me co-host, just so that we can, like admit people if they come.
But you can make.
Am I a host?
Your host.
I'm a host. Good start.
All right.
Well, we have all. So we're happy to have Pradeep from JP Morgan. So Pradeep did his PhD with two illustrious advisors, Alexei and I.
Michael is illustrious.
That's true.
At this prestigious institution of the University of Miami. Now he's going to tell us about his awesome work on certified randomness. This is, I guess, building on this idea from Skyr instead of certifying random numbers from random numbers.
Right. Thank you all for coming. So the talk will be more or less based on the paper that we put out a few weeks back on certified randomness, and this work is like one of the efforts to push theory towards the direction of experiments and push experiments closer to realizing what's probably like correct and doable. So as the title says, a lot of this work was achieved using a trapped ion quantum processor, and that was provided to us by Quantinuum, and it required a lot of close collaboration with the engineers there in making this happen. Also, the work of this scale requires a lot of high performance computing, and that was given to us by DOE labs, specifically Argonne and Oak Ridge. Okay, so let's begin. So this work falls into this overall theme of trying to do beyond classical tasks using quantum computers. So one task that has almost become this benchmark that everybody does is this task of sampling from random circuits. Right? So a random circuit induces a distribution on bit strings, and sampling from this task is expected to be difficult. And in 2019, Google did an experiment, which at the time it took a long time for the best supercomputer in the world to do, and the experiment has been repeated several times. And even our work, kind of the first iteration of this work, started off as an random circuit sampling task, and we had an ion trap machine, and we did RCS at a scale where the best supercomputer at the time, Frontier at Argonne, took about 100,000 years. And one difference between the kind of regime superconducting qubits operate and the kind of regimes we operate in is they usually operate between 65 to 70 superconducting qubits. On the other hand, our qubit count is much smaller, like 56, between 50 and 56. But at the same time, we can do all-to-all gates, which means we can reach similar complexity of circuit simulation at much shorter depth, and which allows us to achieve a much higher fidelity of execution. So these experiments only show one thing, that the quantum computer did something that a classical computer couldn't, and the output are just random numbers, right? So one wonders, like, are there any practical applications of this task? And because these are just random numbers, you could say, okay, like, why not just use them as a random number generator, right? But then, like, we have lots of ways of generating random numbers. You can toss coins, you can roll dice. This would be a particularly expensive way of generating random bits. So what is the point of doing all this machinery, ending up with these random bits? It turns out the kind of randomness you get out of this experiment is special in that it allows for public certification, which is not possible with arbitrary randomness. Okay, so how do we use randomness today? So usually the way computers use randomness is you start with some hardware source, something like CPU jitter or network fluctuations or patterns of user movement, and then you use that seed into you seed a pseudorandom number generator, which stretches it into something usable, right? Which applications consume for password generation, or like a blockchain may use for blockchain operations in doing lotteries, auctions, etc. But this also introduces a obvious point of vulnerability. If, for example, the hardware source is compromised, then everything below that is fails. Right? And you might wonder, like, is this ever an issue? Like, is the failure of hardware entropy a real concern? Well, it's a big enough issue that if you look at Linux kernel and how it handles entropy, Linux does not trust hardware for its entropy sources. It tries to do it as much as in a software level as possible. It turns out like there have been cell phones which have shipped without an RNG chip inside, making several cryptographic tasks not possible with them. So perhaps like this vulnerability in the hardware is not that unheard of. And the other issue that's present with the sources is that you might like have the whole box that generates entropy, but there is no way of checking how fresh this entropy is. Someone might have like plugged in the USB drive with pre-generated randomness, which passes all your tests. But again, these are pre-generated, so there's no guarantee of freshness there. And for certain applications, freshness might be of importance. So the ability to certify randomness has the potential to improve security in many applications. That's one thrust. The other thrust is this issue of remote verification. So say you're playing a game with a partner over a phone. Say you're playing a board game where you trust that your friend is rolling dice fairly correctly, right? But they don't have to do that. They can just lie. They can just lie. Oh, I got 6 every single throw. How do you verify that someone acting at a distance is using randomness fairly? And this is a problem which does not have a classical solution, but it turns out the randomness we get out of our protocol has this feature. And this is important in settings, for example, in blockchain protocols, right? Like, so you have like a lot of money at stake at online auctions conducted by other people who you probably do not trust. How do you trust that they're doing things fairly? In the financial setting, it turns out that if an IPO is oversubscribed, like the allocation gets decided randomly. And again, this needs that you trust the entity doing these lotteries that they're doing things fairly. So the ability to jointly certify randomness has the potential to improve transparency in these applications. I'll pause here for questions if there are any. Okay.
What do you mean by jointly?
Jointly, so there is a version of this protocol where you can assign multiple people can verify independently and then vote on the verification. But you don't have to trust, for example, that. So if only one person does a certification, the obvious failure point is like, okay, how do you trust the verifier themselves? But it doesn't have. You can have like a majority vote, where many people certify.
But is many required? Like if Michael and I both want to make sure it's random, can I be certain separate and he be certain separately, or we need to like collaborate? Like, what if I trust? And I want to verify that
Right.
I don't trust.
So,
Michael.
right. So for example, like in a blockchain, you might have several parties who don't each trust each other. Then you need to both independently verify using some protocol.
It's possible.
It is possible to do
So
that.
jointly doesn't mean that they have to collaborate. Like they can all do it.
They can all do it. Yeah. All right. So here's the key idea. So a quantum computer achieves a high score in sampling. We knew that. We would have known this since 2018, 2019. What is probably a bit less trivial is like a high scoring. If a quantum computer achieves a high score on a sampling task, it necessarily implies that there is some entropy in the bit strings it generates. Right? So effectively, it amounts to showing this connection that proof of randomness in certain settings, in the case of sampling problem, the proof of randomness becomes achieving high score in the cross entropy task if it's above a threshold, or relatedly, like in the task of playing a non-local game, if you violate certain inequality and you prove that something quantum is going on, you can turn them into a proof of randomness. So both of these methods you can leverage it as like a proof of certified randomness, and then it allows you to give you a lower bound on entropy.
You're saying there's an efficient way to verify this?
So this there's no efficient way, no, of verification, right? This is efficient, this is not.
Bell inequality, it verifies the whole sampler?
So so this is like unrelated to the RCS task. There is like entanglement based another protocol, right? And Chris Monroe was doing this in 2008, for example. Right?
This
So-
one is pretty. This bell
Right,
inequality
right.
down.
I think so, they have like an IMS or something. So let's acknowledge.
No, but they have
It work.
they have some randomness beacon.
Yeah, they do, right?
Right.
Are you part of the current?
Yeah, I mean, I think so, I think, yeah, the original vision was the bell experiment, I think currently they have a simpler one.
Mhm.
Should modify your slides to.
No. Like they know. I was at NIST just a couple of days ago.
They didn't complain.
No. Yeah, they're happy. But the obvious issue with like Bell inequality-based violations is that you have to trust the experiment in that, you have to make sure that things are not communicating. There is no other classical communication, and you might mitigate some of these issues with the sampling problem. So what does proof of quantumness look like in the computational setting, in the sampling task? Right. So I have a quantum circuit, which is a quantum program acting on qubits, and it induces a distribution on bit strings. And I measure something called the cross entropy score. And the cross entropy score, in the way I've defined it, it concentrates around 0 if the bit strings were sampled uniformly. But if the bit strings were sampled honestly by actually doing the circuit, then it concentrates around 1. So any positive score in XCB is an indication that something quantum is going on. And there's another regime where you're trying to do things quantumly, but things are noisy, in which case you land somewhere between 0 and 1. So that's a noisy XCB. And now, like just looking at this expression, it's not immediately clear why achieving a high score there should be difficult. But it turns out achieving high score in XCB reduces to this assumption that Scott and others made a few years back, which says that given a circuit, I cannot tell if any particular bit string has amplitude or probability less than 1/2 to the n or greater than 1/2 to the n. So even the task of telling how big or small my amplitudes are, that's difficult, right? There's no efficient classical algorithm to do it. And more details have been worked out on this task. So yeah, so if you had like a classical way of achieving a high score in XCB, you would violate this conjecture.
So does this require this inefficient classical computation on the side to compare it to, or not?
So I mean the verification will be inefficient.
Inefficient,
But
right?
yeah. But now all I'm saying is like, is there what is the basis of trusting that you cannot, like I cannot simply come up with S's in an efficient classical way? And so the conclusion of this is like achieving high score in XCB should be as difficult as trying to compute these amplitudes. There's so some more details on the machinery that leads to the theoretical lower bound. So the assumption I mentioned earlier is that you cannot tell if a bit string is heavy hitting or low or light, yeah, the opposite of heavy hitting, if the amplitude is higher or lower. But for sort of randomness, you need something a bit more exotic. So to define this problem, this is this is done by Scott. So you define this problem where I give you a bunch of quantum circuits, and I give you a bunch of bit strings, and I give you a promise. The strings came from the quantum circuit, or the strings came from a uniform distribution. And I want to ask you which is the case. And the conjecture is that there is no Arthur Merlin protocol to solve this problem in time that's polynomial in n. So meaning that even if you had an all-powerful prover, you could not verify this task efficiently. And with this, like this conjecture leads, this is proven in some settings. For example, the random oracle setting gives a proof of this conjecture. And it can be used to achieve a lower bound on entropy. In particular, any algorithm that achieves high cross entropy consistently over a random family of circuits must generate some entropy proportional to P and Q. But again, note that like here, you need high fidelity and like high consistency, and this puts some stringent requirements on like on achieving this. In particular, if you recall, the first Google experiment on supremacy, they had a XCD score of maybe 0.02, right, something like that. And with those numbers, it's probably difficult to hit this regime.
Would it translate? What were the parameters they achieved?
So I mean, so they did one experiment, so we don't know what Q is, right? Like to know Q, you have to do the experiment many times and see how often you cross the threshold. But P for a single experiment they did was probably like 0.002. The first experiment.
Q was one.
But that was for like a single instantiation, and you have to be able to do that repeatedly. And there's fluctuations around XCB. You may not always cross the threshold.
Right, they didn't show it.
Yeah.
Maybe it's too early to ask that, but like presumably you will be relying on the fact this quantum system is large, right? Like it's a small quantum system, doesn't work.
Yeah.
But if it's large, you also can't compute this XAB. So like,
Yeah, no, it's a difficult task finding this sweet spot.
does it exist?
It exists. Yeah, you can find it. So this is the underlying complexity theory. So now to do an experiment, so I would turn all this into a usable protocol. So what is the protocol? So the protocol has two phases. So there's the generation bit and there is the verification bit. To generate randomness, what we do is so I have a server, which I believe is running a quantum computer, and I throw quantum circuits at it. So I submit quantum circuits C1 to CK, and I expect it to return a sample corresponding to that circuit, S's. Right, so that's my generation protocol. And to verify, what I do is I pass the circuits and the samples I got, and I send that to a classical supercomputer, and I get the score XCB. And if this crosses some threshold, I say, okay, I'm happy with it. Then I can extract entropy from the samples I got. One way this experiment is, say, different from what superconducting qubits often do is usually in superconducting hardware, it's easy to use one circuit to generate millions of samples in very quickly. But that also makes it easier to cheat. In our case, what we do is like every sample comes from a unique circuit that the server hasn't seen before.
So like, it's the same question. How do you know that the thing is there is quantum if you have a classical thing that can do the same algorithm? Like this classical computes the full circuit. So like, why do you think there was a quantum machine there?
Yeah, so I mean, the circuit analysis is proving that there is a quantum machine. Yeah, I mean, it's all coming, Alexei. It's all coming, right? So like Alexei said, like, how do you know that there is actually a quantum machine here? They could have a classical computer doing just simulating the circuits. If
what you're doing there on the right.
Yeah, exactly. They could have another big computer here doing things classically. How do you know this? So you have to demand that to be convince yourself that actually something quantum is happening here. We impose this constraint that the server has to respond very quickly, right? So there is T quantum. I give you a circuit. I want a response immediately. So which means that the circuit has to be difficult enough that a supercomputer cannot simulate it within a short time, right? But what that also means is that circuit is difficult. So you have to spend a lot of energy and compute trying to validate it, right? So again, so like I said, the point of this, one challenge on the engineering side is to identify a circuit family that takes that's difficult to simulate for an adversary, but that's reasonable for you to verify, validate. This task is but remember that the adversary, so if they were trying to cheat here, the adversary has an advantage. When I do my XCB calculation, I have to propagate the circuit to perfect fidelity. But here, they don't have to do perfect fidelity. They can just say, oh, I'm like a device that I operate at 10% fidelity. So they have a much easier task trying to cheat because they can cheat up to some target fidelity. So in particular, the time to spoof would be proportional to fidelity, a number between 0 and 1, and time to simulate, which is the time you would take to validate. And to ensure that there is some security in all this, like the condition that you have to fulfill is the time to spoof fidelity and time to simulate should be much, much greater than time quantum. And as long as you have that, you can tell the two distributions apart. Does this answer your question? That's it.
Yeah, I got it. That's very clever.
Any questions? I pause here. Yes.
Yeah, so here, I guess you require the randomness consumer to trust the link to the classical.
Right. So here we do. I mean, in particular, like I can own this, right? I can have all this inside here. But there is a way of doing this, using delegated computing where you don't necessarily have to trust supercomputer. Yeah. But the easiest setting is where they're like the same person, for example.
And this is something you can like only do with small quantum circuits, right?
Exactly. Yeah. So and this is like another point where it diverges from normal RCS, where in that regime you want to be as big as possible, right? Like here, no, we need to be able to validate.
So wonder that whether this security is exactly guaranteed or is more practical that you are maybe.
So it is practical. So I mean, the security to say anything concrete about security, I need to assume what's the biggest adversary I can threat against. So it's a very concrete statement that puts a bound on practical computation. Yeah, I'll get to it.
If you just have a spoofer who just has more and more compute,
Yeah, if your spoofer has infinite compute, none of this works because time to spoof. If you had like infinite number of GPUs, this takes like you can do it instantly, right? Like, so it doesn't work. So your spoofer, you need to put a bound on how big the spoofer can be, right? So in particular, I'll give the numbers. So these are our numbers in totality. So 56 qubits. It takes me 2 seconds to get a sample. I give you a circuit, I get a return in 2.15 seconds. But if I were to simulate it, if I use Frontier, which at the time was the biggest supercomputer in the world, if I use all of Frontier, it would take me 100 seconds to simulate a single amplitude. Right, and over this circuit ensemble, we have a fidelity of 35%. We measure an XCB of 0.32. So in our condition, so there's a gap between how long it would take to do quantumly, how long it would take to do classically.
what's known about the algorithm that you use on the right, this classical algorithm? What if there's like a slightly better classical algorithm? Then they're all exponential, but what if there's a better exponential?
So So exponential, sorry, like improved classical algorithm helps not just the adversary, but also the verifier.
I know, but what if you don't know it, but the other guy
Yes,
knows?
that's an issue. Yeah, and we spent, yeah, you know, like a lot of time trying to optimize what's the best you could do. Yeah, so
Can you prove like bounds? Like you cannot
You
prove like
cannot-
this,
you cannot.
you have to assume how powerful they are. Maybe just they're hiding a really big secret, they can't do anything.
right.
But can you prove that your algorithm is within some factor of optimal?
I mean, so the machinery we use is just tensor network contraction, and I don't think there is a lower bound on, you know, how best you can do it. At least I don't know the lower
But
bound.
it's a possible thing to like to ask for.
It would be great if it existed.
What are the structure of these circuits that on is going on?
So on over 56 qubits, we have a depth 10 all-to-all gates. So it's about 280 entangling gates. And a circuit is so we come up with this family, and then we try to optimize, you know, the best tensor network path of doing this. And our like we spend a lot of time trying to get this number down. So 100 is the best we could do.
The verification that you do on this supercomputer, that requires like full fidelity, right? You know how to do that approximately. So then, like say there's a faster algorithm out there. What if there's a faster algorithm that works for lower fidelity, but it's
That's also a possible vulnerability for sure. Yeah.
But in this like relationship between like fidelity and time to simulate, that's like sort of multiplicative.
Right.
That's sort of just heuristic. I
Right.
guess.
Yeah. And there could be, and also like the other assumption I'm making is that, like the amplitude calculation and sampling, I'm using the same algorithm, but I could be using a different algorithm to do sampling other than verification. Yeah. And we point all these caveats out in the work, yeah, for sure. Yeah. And we believe like the like if we do subsequent iterations of this algorithm, I think the numbers are going to be much better.
Do you think all these caveats sort of don't make it like it's still useful compared to these other caveats about this entropy in the hardware? Like are these caveats
Well, I mean, yeah, this is the first.
worrisome than the other
Right.
ones?
I mean, no, potentially, right? Like, I mean, we would not recommend this. You use this for high sensitive, like, you know, applications for sure. But again, this is the first of its kind, and maybe the numbers will be better, right? And again, so to answer the earlier question, so my security is against an adversary that's 4 times more powerful. So I assume that, okay, it's like I have Frontier, but my adversary might have something that's 4 times as big. But the probability that they have, so I execute 30,000 circuits, which means I have 1,000,000 bits, million raw bits, but I can only certify this much amount of quantum entropy. Everything else I don't count. And the probability that it has less than this amount of bits is like upper bounded by 10^-96. And in practice, you probably want like a, you know, much higher guarantee in security, in addition to all this like problems with the adversarial model. Any other questions? Oh, sorry.
This is going off Phil's point, like, wouldn't you have to have like tried spoofing this whole thing with just like a low fidelity classical simulator? Like you could just have like an efficient low fidelity classical simulator as like
Right.
as your quantum device. Like, did you check that to see if it would all work?
So if you had like a low fidelity simulator on this side, you can check. So say your effective classical fidelity is 0.1, right? Like that's a classical low fidelity simulation you could do, but you measure XCB 0.3, which means that it would be unlikely for you to get the score just using the classical low fidelity data.
But let's say you had it do the same fidelity as
I mean, so that's assumption, right? So we think that's not that unfeasible, as long as you have your computation powers bounded by this and bounded by this. Running the circuits to this fidelity in 2 seconds is not feasible, right? So the quantum time puts a bound on how best the adversary could have done low fidelity simulation. So because they only have 2 seconds to do whatever algorithm they want to run.
Can you comment on sort of how this compares to this randomness beacon? So here, you need to assume that you have access to this trusted classical computer, right? That's not fooling you. But I guess in this randomness beacon, you also need to like assume that I guess either you trust NIST, do their loophole-free spell test.
Right. So verification is a problem. Like, so it's expensive. One way NIST beacon could benefit from this is you could release this entire transcript. Like, I can verify that the beacon outputs were actually generated from quantum computer if I had the classical compute with me. Like, so, but again, like, there are versions of this protocol, the Mahadevan protocol, for example, which is efficiently verifiable. So maybe in that iteration, you could put it into beacon that anyone can verify.
Oh, somebody could like later do it.
Somebody could later do it, exactly.
Long time has passed and you can still verify. Oh, that's-
So I'll come to one thing. So this is 2 seconds, and when I show this number to superconducting people, they often like scoff at it because they can do things at microseconds or nanoseconds regime. Why is this number so big, especially for quantum systems? I mean, one reason is because this is all done remotely. All of these are remote connections. Like, I'm sitting in New York, this device is in Colorado. Network latency is about hundreds of milliseconds. So the number probably could not get better than tens of milliseconds. In particular, like even trying to get this number down was difficult. So right now, the way things are set up is when you submit a circuit, so that's when I start my timer, and it gets to the internet, gets to the machine, and the circuit has to be compiled into laser pulses and all these transport movements for ions. That takes a long time, and only after the compilation it executes, and then finally I get the result and I stop the timer. If I did this like this using the sequence, it turns out it'd take me like 12 seconds to get a sample, because compilation takes about 10 seconds, even though the ions itself are very quick. And 10 seconds would kill this algorithm because now I won't have that gap between spoofing and verifying. So the solution we do is we do something called like a batch compilation where instead of submitting one circuit at a time, I submit maybe 10, 15, and I do all the compilation. This happens on the quantum server side. I do all of this at the same time, and then I execute serially because I only have one quantum computer. And using this, I can reduce the time much, much lower. So I can get 30 samples in 60 seconds. Right. So this is like just the device engineering, if anyone cares. Maybe already a more interested adversarial model, right? Like, so what kind of adversary I'm assuming? How do I come up with this bound? So the adversarial model is very simple, and the reason it's simple is that when we can do things, prove things about the simple adversary. So what I assume is, so I submit total of say M circuits, and I get M responses. But the adversary has, let's say it has a quantum computer, like a very good quantum computer, the high fidelity, and let's say it also has a very powerful classical computer. So every time, so adversary chooses out of M circuits Q, one on a quantum computer, and it chooses the rest on a classical computer. Every time it uses a quantum computer, it gets a high fidelity output, but it has to do a quantum measurement, right? So the output will have some entropy in it. But if it chooses to use a classical computer, depending on how powerful the machine is, it can get some low fidelity output, but it's a classical machine, so you can do it in a way that adds zero entropy to your responses. And the goal of the adversary will be to give me the responses that pass my XCB threshold while using quantum computer as few times as possible while trying to minimize Q. That's the goal. So the condition is like pass XCB, minimize Q. That's the adversarial model. Right. And now, and to be able to, so my task as a client is, I get the bits, I measure XCB, and from that I have to infer what Q could have been. And the reason I can do this is like a bit string drawn from a classical computer and a bit string drawn from a quantum computer that tend to have a difference in characteristics. In particular, like a sample that comes from a classical computer, if it has low fidelity. So here I'm plotting, so SJs are drawn from low fidelity classical or quantum, and I'm looking at the probability, which is the weight. It's like how heavy is this bit string. If I do it classically, my weights are going to be very low. So this green line is a completely classical, completely uniform distribution. If I sample honestly using a quantum computer, then my bit strings are likely to be heavy hitters. Like I'm more likely to see things that already have a higher weight, right? So my distribution peaks. And if I have like a lower fidelity machine, like I interpolate between this and this. And this all worked out, the details of these distributions. And for any given value of Q is the minimum number of quantum samples in my data, we can have a theoretical distribution of XCB. What this means is I can determine this distribution of XCB for different values of Q. So if my adversary was using Q equals to 0, which is no quantum sample, all classical, then my XCB would be this red line all to the left. If my adversary was, sorry, yeah.
I just want to ask a naive question. So you mentioned this classical machine cannot generate entropy. What does it exactly mean? For example, if I sample from some high entangled paper circuit, I can generate sample which corresponding to true quantum circuit with very high.
So I mean, and you can seed your classical processor. It's a classical processor, right, which is doing tensor network or something, and you can run things deterministically there. In other words, like I will not accept any classical sources of entropy. Your machine might be doing things honestly. It might be, using local entropy correctly, but as a verifier, I can only trust entropy if it comes from a quantum machine, and I don't trust the classical entropy.
How do you tell this entropy? Imagine I have a paper circuit with very high entanglement. I can fully sample this classical.
I choose my circuit family such that you can do that, right? Like, I know that it takes you a long time to generate samples from my circuit. Yeah, if I use Clifford, then nothing would work for sure. Yeah. I can't tell, right?
So actually here you're restricting your classical strategy such as it's just very general.
Yeah, the classical strategy is restricted, yes, for sure. Yeah. But it's just a mild restriction, right? Like, because what else can you do short of trying to predict the probabilities of your amplitude? But yeah. So the complexity theoretic arguments, they assume a general quantum strategy, which may not involve doing this contraction. But to get these numbers, we need to assume something about the adversary, and this is what we came up with. So it's going back to right. So depending on how quantum my adversary is, I get this different distribution. So if Q was small, my XCB would be here. If Q was large, it would be here. So say I get some XCB that a score of say 0.48, whatever. Then I can like using my knowledge of these distributions, I can tell what is the minimum Q such that only with a very low probability would the adversary get this score, right? So I would like say, okay, like a distribution that maybe concentrates here, that sets my the amount of quantum samples I like in my total results. Yeah, so for a measure value of XCD, like I can calculate this probabilities, and we choose Q such that only it's very unlikely that the adversary would have gotten this XCB score by chance.
So going back to the previous slide where you mentioned that to reduce the time of simulation and the time of computation on the computer side, you give multiple samples. Right. To the gap. So why can't you just give as much as, just make this gap bigger and bigger, but give it more sample? Is it because of this kind of adversary?
Why not make this get bigger?
Bigger and bigger, yeah. Instead of 30 circuits, for instance, do 3,000 circuits. Right? So
There's a hard reason for that. Okay, so when I submit a batch, I have some error detection mechanism that tells me if the batch succeeded or failed, right? And a batch may succeed or fail. And if it fails, I reject everything at once. So if I send a 3,000 batch circuit, and if that fails, I lost 6,000 seconds of device time. Right?
So it's not an algorithm.
It's not a problem.
It's not like this kind of adversary, because then I can say that like if you have 1,000 circuits, maybe you want to simulate like 2,000 or 1,000 thousands of them.
Exactly, yeah. Nothing stops analysis from, nothing breaks if I submit everything at once, yeah, right. I mean, exactly, so the way adversary chooses to allocate resources among everything, it does not matter.
Nice.
Right. Anything else? Okay, so and having decided what the minimum Q must have been to get some XCD, then I use a randomness extractor to extract like my final randomness. Any questions so far? I'll say a few things about the verification side. So we calculate XCD using tensor network contraction. So I want to compute this amplitude, and I have a circuit, and make a tensor network and simulate. And one question that people often ask is, what if someone discovers a better algorithm that Alex just did for calculating these amplitudes? But of course, improved simulation algorithm helps both the adversary as well as the verifier. So now the verifier can make circuits a bit more difficult. You can submit a bit instead of 30,000, I can submit 50,000 challenge circuits. Public awareness of improvements with neutralized gains on both sides. It becomes difficult if knowledge is asymmetric, right? Therefore, if you have a better algorithm, you should keep it to yourself. Do not tell your friends or publish papers. And the other question is so we did some HPC work. How good was this HPC work? In particular, even without inventing new algorithms, can I be clever by, say, software engineering and trying to make this better? And we think it's a little difficult because we did spend a lot of time trying to find optimal simulation strategies. So we used 4 supercomputers, and we had experts from all of these places helping us come up with the strategy. All of these machines have different GPU profile, and we optimize tensor network for each of them independently. And we achieve a pretty good efficiency. So just because you have a GPU doesn't mean you can use it to 100% its theoretical power, because each algorithm has numerical efficiency issues. But these numbers of 49, 64, 60% on this GPU, these are pretty good compared to what others have done. And so we did spend a lot of time optimizing the tensor network contraction for these models. And even at full HPC scale, we achieved something called strong scaling, right? So if I used 800 GPUs, and if I use 8,000 or 80,000 GPUs, my time to simulate is strongly linear, meaning that I'm as parallel as I can possibly be. There's very little memory or other overhead going on there. And across entire machine, 45, 15%, that's remarkable. And in particular, we have our compute resources. We achieved this computation of 1.1 exaflop, which is 1 exaflop is a threshold these days for high performance, really high performance classical compute, and we're safely in that region. So it'd be difficult to using our algorithms to do this much better. Any other questions on the? Okay, now I'll say a few things about application. So now we have this technology, right? But where can we use it? And the answer isn't clear. We have a vague sense of like what are potential the characteristics of problems where this may be useful. For example, it helps with whenever you need classical remote verification among untrusted parties. Where would that be useful? And one example people have like pointed to us is in blockchains, for example, and we're digging into it, seeing if it's useful. There's another issue, right? Like, and there are other classical algorithms for people to agree on randomness without using a quantum computer. There are things that these are called coin flipping protocols. They exist. One thing you get out of this, which you could not do classically, is we get a randomness expansion. So you could start with a weaker seed, and then you end up with a much like a longer length. So we have these three things that we think are together are new, that which prior algorithms couldn't provide. And now we're on the search for possible application areas where this would be useful. And I was at like the MIT Media Lab recently, and the Bitcoin people are very excited. They're like, oh, they'll solve a lot of problems in Bitcoin if certain things were worked out. Right. So a couple of things on Outlook. So there's a lot of room to improve on the protocol. For example, the time for quantum samples right now is 2 seconds, but most devices operate really at megaseconds regime. So and we think we can cut down on this by simply improving classical compilation, things like that, and hopefully we'll improve this in subsequent versions. Fidelity will improve. A week after we did the experiment, the machine just like improved 50% better. So we think fidelity is getting in a much better shape. And potentially in the future, you could defend against much larger adversaries at like supercomputer scale using much smaller resources, using a small GPU cluster. Also, even like outside of our implementation, there exists version of this protocol where generation as well as verification is efficient. We can't do that right now because they need fault tolerance and all that stuff.
So what's this efficient?
Like Mahadevan, this is the trapdoor claw free for function-based protocols, right? But even if we like say could implement this, then the question still exists. What applications would benefit from it? Are there applications at all? And especially for us now, we're thinking about are there applications which not only benefit but can also realistically tolerate this inefficient verification problem.
Is it obvious that there's no efficient version that doesn't require fault tolerance? Like Scott kept giving talks about these peaked circuits. Like, what if you find these peaked circuits? Could they also be like enough to give randomness? Is there a no-go?
There is a no-go. There is no no-go. Yeah. Right. There is no no-go.
The current circuits are too big.
Sure, but like, could there be like clever choices of circuits and clever choices?
There's limits on the key size of the.
No, I'm just saying there could be like a different approach, like with special circuit and special measurements, that you could in fact like efficiently verify and nevertheless have the randomness. Because there's no no-go for that, right?
You know, so but like there is some kind of complexity reasons why this may not be possible. For example, if you could do things efficiently, classically, it would imply BQP with quantum advice is probably as powerful as BQP with classical advice. So things like that would be like the consequence of being able to do that.
But how about this idea, Scott's idea of these peaked circuits, right? So
how does he verify? What's the method there?
just there's somehow,
Right.
unlike in these random circuits, there's like some signal that can actually be verified, like with a view.
That's more of a conjecture.
Oh, yeah, it's totally conjecture, but I guess there's no go.
There's no
construction.
No, yeah, there's no construction, but I don't think it's just, you can say, oh, complexity theoretically it's not possible.
I can't say it's possible. Yeah, I have a feeling against it. Maybe there's some other issues will come up, but yeah. So that's sorry. Yeah, please.
Yeah,
No, I mean, this is the last slide, like, I have all the numbers here. So there are three fronts, I think, which really make this possible. A very high fidelity at like this gate depth, 32%, XCD, that's pretty significant. And second, there was a lot of work trying to make it so that there exists a gap between time quantum and time to validate. And like being able to access this kind of supercomputing power and being able to reach this kind of classical processing speed makes this possible. On the theory side, there's some nuances which we cleared out. So the original protocol by Scott, it was meant for superconducting qubits where you give them one circuit and you expect 1 million samples in return. It turns out like modifying the protocol to get one sample from one circuit, it requires you to redo the whole analysis from scratch. So we bridge that gap and we have another complexity proof that achieves the same lower bound in our setting. So that's the paper, and so that's the main paper. And we also have some very high level thoughts on what applications could be useful. None of it is particularly fleshed out, and that's our future direction to work out the kinks. Yeah.
So you said that one of your complexity theory assumptions was justifiable in the random oracle model?
Yeah.
Could you expand on that?
So if you had access to a random oracle, you could reduce this task of telling circuits apart to some Boolean function, and you can show that like LLQSV is in the QIP to that class, and something happens.
So what exactly is the random oracle modeling?
So given a Boolean function, I'm trying given the random function, I'm trying to sample from the Fourier spectrum of it, something like that. And being able to identify the higher Fourier weights and low Fourier weights apparently is a difficult problem, and it would solve that.
Are you modeling circuit itself, the random circuit itself, as a random oracle?
So I encode the random oracle's output as a quantum circuit. Right.
Oh, okay. So you're assuming you have the ability to build a circuit out of
random oracles. Right.
Oh, okay. I mean, that sounds like something you could actually do, right? I mean, you don't even need to make the assumption, which we would just do that.
It's difficult to construct states that have that property with everything being a random uniform distribution randomly. This is much easier for us. Right.
Can you use this time and balance trick for like verifying other things? Like suppose I want to verify a quantum simulator and I ask my quantum simulator to answer like billion questions about, lots of different circuits and lots of different observables. And then I take, whatever, half a year to check like a couple of them.
Yeah. You could probably use it for other things, yeah, for sure. Yeah. Like, I mean, one thing we know that comes out of this.
Yes, that's what we're doing, man. Exactly.
The one thing that comes out of this is position verification, right? Like, so I can use this to verify that, so I know some submarine somewhere, and I give it the circuit and expect an output, and the time quantum kind of sets the radius of how far this thing could have been. So I can verify position in some sense using this protocol.
You were saying you had a question?
Yeah, so if, so you mentioned superconducting qubits and the modification of the algorithm. So if you wanted to do the same experiment with superconducting qubits, how long that time would have become?
So my microseconds, I think like the time would improve maybe 10 to the -3 by improvement, 10 to the 3 improvement in latency. But at the same time, you lose on fidelity because the individual gets expensive, plus to achieve the same difficulty of simulation, I need to go much deeper because entanglement spreads like slowly in those machines. Yeah, so the reason you couldn't do this with the first supremacy data is that the quantum data looks almost identical to the classical data, and in our work it's very important to be able to tell the difference apart confidently. You couldn't do that with the first experiment. Yeah.
sense. So I think in this work actually we hope to in a very sweet spot regime, such as in fact your circuit is actually classically simple, but it take much more time than you need this quantum ones. And under this assumption, we can actually tell that you cannot really do it in finite time. But I want to mention that this might even this might not really be necessary. So I mean, in the machine learning community, you can there could be such a strategy that assuming this adversary knows what kind of random distribution you want to do. Then maybe 1 year ago, it begins to sample. It begins to classically, which take 100 seconds to run. It gets a lot of sample shots. You can actually learn some kind of machine learning model, which try to predict such shots using the XCP as a loss function.
Right.
And when they really when you really give it this real time, circuit classical description, it knows that. I mean, you actually use this kind of machine learning model to influence what is the outcome.
I mean, right.
Contract.
You're absolutely right. I mean, there might be other strategies outside of contracting to cheat, right? The problem with machine learning algorithm, what you said is like, it might be difficult to enumerate all possible circuits you could train in beforehand. And if an algorithm, like you said, existed, it would seem to violate the conjecture I began with, right? Like where there is no efficient classical algorithm to tell.
Wow.
Right, just saying to pre-compute the stuff that you're going to compute later.
Take a long time, then you inference.
Right. I mean, the question is like how much time would it take to pre-compute, like a billion possibilities of circuits, and it probably becomes unfeasible. But it'd be fun to study. If you could write a ML model to do this, that'd be great.
I think there are some existing work. I'm doing some actually GPT as a sampler.
GPT sampler on that'd be great. I wonder like if you can make it work with GPT. Sure.
Can't you move the compilation to user side to reduce the?
You could. You can to some extent, like so there are certain things like ion movements which you can do before. There are certain things like laser pulses which need immediate feedback of the machine at that point, which you cannot offload on the client side. But it seems that you could even get rid of this compilation altogether and just do things on the fly as you get the thing. So we expect the compilation overhead to possibly go to 0 in the near future.
Okay, any other questions? Anybody on Zoom? Thank you very much for your nice presentation. Questions?
Stop sharing.
Can you stop recording?
You don't start it? Oh, I didn't start it, but I can stop it. Wait.